Hi again, and welcome to this hands-on practice session for neural networks. And let's start with the data part, the essential important part for training any machine learning model. Typically, a neural network's parameters are initialized or, let's say, created as small random numbers. Neural networks often behave poorly when the feature values are much larger than parameter values. Furthermore, since an observation's feature values are combined as they pass through individual units, it's important that all features have the same scale. For this reason, it is best practice, of course not always necessary, uh, to standardize each feature such that the features value have the mean of 0 and the standard deviation of 1, and this can easily be accomplished with scikit-learn's standard scaler. Here, let's see how does that look. So what I do first, I import the pre-processing from scikit-learn and NumPy. I create some feature set, so this is just some numbers. And then it is as easy as this. So a scalar, we need to create a scalar. It is a standard scalar from pre-processing. We initialize that. And then we have the feature set here. We have our scalar here. And then we need to do this. We fit the transformation and the features. And these are the features we got. And to check that it is what we wanted, we want to check the effect of standardization. We check the mean and the standard deviation, and yes, mean is 0 and standard deviations is, well, technically 1. So this is how we do the pre-processing and the standardization for a neural network to begin with. After that, we want to design a neural network, and for that, we use Keras, as I said, and we use a sequential model. So basically, from Keras, we import models and layers, and then we tell the machine that our network is going to be sequential, basically have several different layers. If you remember, neural network consists of layers of units, and there is incredible variety of top-level layers and how they can be combined in network architecture. For now, there are commonly used architecture patterns, and the truth is that selecting the right architecture is mostly an art and the topic of market research. But to construct a feed-forward neural network in Keras, you need to make a number of choices. You need to decide each unit in the hidden layers receives a number of inputs, weights each input by a parameter or value. This is what's happening in a neural network. Sum together is all weighted input along with some bias, then most often apply some function called an activation function and then send the output to the unit in the next layer. So this is how a neural network works. Once again, receive the input, weights each input, sum together all the weighted input, then applies activation function, and then send the output in the next layer. So first, for each layer in the hidden and output layers, we must define the number of units to include in the activation function. And this is what you are seeing here. I add a layer, and here I'm adding a dense layer with 16 units and an activation function that I said is going to be relu here. Overall, the most units we have in a layer, the more units we have in a layer, the more our network is able to learn complex patterns. However, more units might make our network overfit, if you remember from the video lecture. For hidden layers, a popular activation function is relu. And then to define the number of hidden layers, so that was the number of inputs, we define now the number of hidden layers. More layers, again, allow the network to learn more complex relationship, but there's a computational cost. And we have to define also the structure of the activation function of the output layer. And the nature of the output function is often determined by the goal of the network. And it's, for example, if we have binary classification, we could have sigmoid activation function. If we have multi-class classification, we could use softmax activation function. For regression, actually one unit with no activation function, and we also need to define the loss function, the function that measures how well a predicted value are. And this is again determined by a problem for binary classification, for example, binary class entropy. For multi-class classification, categorical cross entropy, or for regression, mean square error. And then we need to define an optimizer, which intuitively can be thought of as our strategy, walking around the loss function to find the parameter values that produce the lowest error. And there are some common choices, like stochastic gradient descent, root mean square propagation, adaptive moment estimation. And then we need to select one or more metrics to evaluate the performance, such as accuracy. And Keras offers two ways of creating neural networks. Basically, Keras sequential model creates neural network by stacking together layers, and then an alternative way is functional API, but this is more for researchers, not for practitioners. So we are sticking to the sequential model, stacking the layers on top of each other. And in the solution that you see here, now let's get back to the code. We created a two-layer neural network, and when we count the layers, we don't include the input layer. So this is the input layer. Forget about that. We don't count it. I mean, it matters, but we don't count it. And then we have two different layers. Each layer is dense, and by that I mean it's fully connected, so everything is connected to everything, from first layer to second layer to third layer, meaning that all units in the previous layer are connected to all units in the next layer. And in the first hidden layer here, we have 16 units, meaning that that layer contains 16 units with ReLU activation. And in Keras, the first hidden layer of any network has, this one, has to include the shape, as you see here. And then that is input shape parameter, which is the shape of the feature data. For example, 10 comma tells the first layer to expect each observation to have 10 feature values. Then second layer is the same as first layer without the need for the input shape parameter, as you see here. So I basically repeated the same thing, but I didn't include the shape. And the network here is designed for binary classification. So the last layer has a sigmoid activation function, which constrains the output to between 0 and 1. It's kind of probability. And so this is basically the architecture of the model. So I can compile that. And then what we need to do here before training our model is to tell Keras how we want our model to learn. We do this by using compile method with our algorithm, with our optimization being RMS probe, and the metrics that we want to evaluate our performance is accuracy, and our loss function is binary cross entropy. So this is basically how you design a network. You say it's a sequential, add your layers, number of inputs, activation function on the output layer, and then You define the loss function, the optimizer that you're going to work with, here root mean square propagation, and then the performance metric, that is the accuracy here. So this is generally how we design a neural network. So let's see how it works really. This is the general architecture. You can use it for several different things, but let's try it on an example. And I'm going to use it on an IMDb dataset that is available in Keras. Of course, this code is going to be available in the description box on YouTube channel. And then from that, you can go to the GitHub page and download the code. But this is the thing that you could also do yourself. You can get the dataset. And specifically here, we use 50,000 movie reviews, 25,000 training, 25,000 holdout for testing. I know this is crazy, the numbers, not a standard thing. Then categorize as positive or negative, so it's a binary classification. And we convert the text of the reviews into 5,000 binary features indicating the presence of the 1,000 most frequent words. Put more simply, our network will use 25,000 observations, each with 1,000 features, to predict if a movie review is positive or negative. And the neural network, but let me do this first. So these are the things we need here. We import NumPy again. Of course, it has been in this notebook, but I just say it so that it is from scratch. We import the IMDb dataset from cross datasets. For pre-processing, because we're processing text, we import tokenizer, again models and layers. And number of features, as I said, is 1,000. Okay, and I'm going to load the data set here, and as you see here, I'm going to do the one hot encoding to convert the text to the binary by tokenizer. So let's run. Come on, yeah, that's it. So, and now we designed we have basically got whatever we wanted, loaded the data set, training, testing. And now we are going uh, to train our neural network, basically. So this is as before. We have the sequential model, 16 values. I mean, it's exactly the same model that I said before. Okay, and this is where we want to train our our data set. And in Keras, we train our neural network model using the fit methods, and there are 6 significant parameters to define. The first 2 parameters are the features and the target vectors. Basically, what are the features for input value and what is the output value that we are uh, we are uh, we are using. And then after that, uh, the epoch parameter defines how many epochs to use when training the data. Verbose determines how much information is outputted during the training process, with 0 being no output, 1 outputting the progress bar, and 2, 1 log per epoch. Batch size sets the number of observations to propagate through the network before updating the parameters. And finally, we hold out a test set of data to use the evaluate model. And these test features and test target vectors can be arguments of validation data, which we will use them for evaluation. Alternatively, we could have used validation split to define what fractions of the training data we want to hold out for evaluation. And in scikit-learn, the fit method will return a train model, but in cross, the fit method returns a history object containing the loss values and the performance metrics at each epoch. So let's see. Yeah. And this is only, I put 3 epochs here. And the training is completed, and this is a loss function on training dataset, accuracy on training dataset, validation loss, and validation accuracy. Making prediction is easy in Keras. Once we have trained our neural network, we can use the predict method, which takes an argument as an argument a set of features and returns the predicted output for each observation. In our solution, our neural network is set up for binary classification, so the predicted output is the probability of being class 1. And by that, I mean observation with predicted values very close to 1 are highly likely to be class 1, while observations with predicted value very close to 0 are highly likely to be class 0. For example, let's see here. This is like generally doesn't really help you much, but here you can see the predicted probability of the first observation in our test feature matrix to be in class 1. So you see, this is what you're seeing here. Class 0 I put here, so class 1. Yeah. Okay. So this is how we predict a value. We also want to find the, let's say, sweet spot in the network's loss and accuracy score. And this is how we do it by using matplotlib to visualize the loss of the test and training set over epoch. And this is basically, we create a history version and then we visualize. And this is what you see, the training loss came down, the testing loss came down, but it went up again after 200 epochs. There is another way of doing that also, is we can also do the visualization for test accuracy over epochs, each epoch. And this is what you're seeing here. And you should keep in mind that when our neural network is new, it will have a poor performance. As a neural network learns on the training data, the model's error on both the training and test set will increase. However, at a certain point, the neural network starts memorizing the training data and it starts overfitting. And when this happens, the training error will decrease while the test error will start increasing, as you saw here. And so we need to find some approaches to solve this overfitting problem. One way to avoid overfitting or to reduce overfitting, as you already saw in the previous video lectures on neural networks and best practices, was to use weight regularization. And basically, as I said there, it is penalizing the parameters of the network, so they tend to become a less complex model. And I again loaded the libraries that I needed. The new thing that I imported here is basically the regularizers from Keras. I also imported that. And then this is exactly the same thing. I loaded the data and I'm going to start the my neural network design, and it is exactly as you saw before. The only difference between the previous model is that we can add a weight regularization by including here and here kernel regularizer, and this is an L2 regularization. In this example, 0.01 determines how much we penalize higher parameters values. So let's run this and we train For some reason I put more epochs here. Now we have 20 epochs. And you already see the loss function. The loss value is getting kind of smaller. Okay. Now let's see. This looks this time. See, it looks better. So the test loss is coming down. So our regularization paid off here. But this is not the only approach. There are some other approaches as well. There is another way also for reduce the overfitting, and that is earlier stopping. By earlier stopping is trying stopping the training when the test loss stops decreasing, and this is, as I said, the strategy that is called earlier stopping. And as I said before, typically in the first training epochs, both training and test error will decrease, but at some point the network starts memorizing, and then that is when we want to stop the training process. And this is quite easy in Keras. We can implement earlier stopping as a callback functions. And callbacks are functions that can be applied at certain stages of the training processes, such as at the end of each epoch. And let's see how it looks here. I mean, as before, we just import the necessary libraries, and what I do here, I'm importing to different things that I need. I use earlier stopping mailing here, but in another approach, I use model checkpoint too. So from cross callbacks, we import earlier stopping and model checkpoint. And this is exactly the same design, network design that we had before, so nothing has changed here. And then I loaded the data, and this is the same structure as before. And we now set the callbacks functions to earlier stopping and then save the best model. Specifically here, we include earlier stopping that monitors loss functions. And what we are telling it is that we want to define that our model monitor the test, that is validation loss, at each epoch, and after the test loss has not improved after 2 epochs, so that is what the patience means, training is interrupted. However, since we set patience equal to, we won't get the best model, but the model 2 epochs after the best model. Therefore, optionally, we can include a second operation, and this is why I have this model checkpoint here, which saves the model to a file after every checkpoint, and then which can be used later, and it would be helpful for us if we set save best only true, because then the model checkpoint will only save the best possible model. So let me run this, and then the rest is more or less the same. And this is the thing that you need to notice here. The number of my epochs was 20, but it has stopped at 6. So basically, and you can see here, so this has started, accuracy has started dropping, and oops. So you see, this is the best lost value. It waited for 2 epochs, and since it didn't improve again, it stopped the training. So this was another way of doing reducing the overfitting. Another approach to reduce the overfitting is by using Dropout. And Dropout is a popular and powerful method for regularizing neural networks. In Dropout, every time a batch of observation is created for training, proportions of the units in one or more layers is multiplied by 0, and that is where the dropout terms come from. They are dropped. In this setting, every batch is trained on the same network, the same parameters, but each batch is confronted by a slightly different version of the network's architecture. And dropout is effective because by constantly and randomly dropping units in each batch, it forces units to learn parameter values that are able to perform under a wide variety of network architecture. That is, they learn to be robust to disruptions in other hidden units, and this prevents network from simply memorizing the training data. It is possible to add dropout to both the hidden and input layer, and when an input layer is dropped, its feature value is not introduced to the network for the batch. A common choice for the portion of units is to drop 0.2 for input units and 0.5 for the hidden unit. And let's see how it is done for it in Keras. I load again everything, data, and we get to the network architecture. Model is sequential, and basically it's more or less the same, but we have these feature layers. Drop out 0.2 for input, 0.5 for the next for the rest of the layers, and that's it. Let's see how it works. And this time, so since we don't have early stopping, it's going to run for all 20 epochs. Okay, and now you see the test loss is behaving the way it is supposed to behave. Okay, there is one more thing that I want to tell you before wrapping up this hands-on practice, and that is about saving your model. In when we're talking about early stopping, you saw that we use model checkpoint to monitor and early stopping to end the monitoring and end the training when the test errors stopped improving. However, there is another way that we could use model checkpoint. In real world, the truth is that it is common for neural networks to train for hours or even days, and many things can go wrong during that day. I don't know, computers lost power, servers crash, and so many different things. So with using model checkpoints, we can solve this problem, but saving the model after every epoch. Specifically, after every epoch, model checkpoint saves a model to a location specified by the file path parameters. Uh, and if it only includes the file name, that will be overridden with the last model every time. But you could have different approaches. You could also save the best model, as you saw before. Let's see how is it here. So basically, I set callback function. I mean, everything else is the same. Training, designing the network, and now I put this checkpoint here, and I want to save the best model, basically. And this is as easy as that. So I'm going to save the model somewhere in the path that I have given. I shouldn't have given 20 books here because this is not really the point. Okay. But while that is running, let me tell you that there is another interesting thing that we can use with Keras, and that is that Keras provides utility functions to quickly visualize neural networks. If we wish to display a neural network in a Jupyter network, we can use model to dots, and the show shapes parameter shows the shapes of the input and output and can help with debugging. And for simple model, we can set show shapes equal true. And we could also describe our network architecture simply as you see here. So basically, this is how our network architecture looks like, and that is very useful when you're doing the reporting. And by that, I conclude the hands-on practice and generally the video lectures for this week. You're going to have a mini project using neural networks, so make sure to go through these practice again if you need it, and good luck with your project. Bye and see you next week.